Hello everyone, this is Sherry Sahibi, data mining class, and we are going to talk about deep multi-layer perceptron or deep MLP. So the MLP that we have seen so far, the multi-layer perceptron that we have seen so far, only had one hidden layer. So it was one input layer, one hidden layer, and one output layer. Now, when we have a network MLP with more than one hidden layer, then it's basically multi-layer perceptron, and when it gets to hundreds of layers, it's basically a deep network, a deep multi-layer perceptron. So what is the structure of deep MLP? You can see that here. So what we have is that we still have our input layer. So this is our input layer. And then we still also have our output layer. This is our last layer. So we have P neurons in the output layer and D+1 for augmentation neurons in the input layer. And then in between, we have H different hidden layers. And in MLP, what we have is a fully connected network that you can see that all the neurons in each of the layers, except the augmented ones, are connected to all the neurons in their next layer. So or the previous layers. So it's basically fully connected. For the augmentation or bias neuron, we can see that it's only connected to the neurons in the next layer, but still all the neurons in the next layer that are not bias neurons. Okay, so this is a fully connected and also feed forward network. Why is it feed forward? We have learned that it is feed forward because to calculate the output, we start from the input and we just move forward and we can calculate the output according to that. So to summarize this kind of network, again, what we have, like blocks, what we have is an input layer X, and then we have some hidden layers in between, let's say Z1, Z2 until ZH, if we have H different hidden layers. And finally, we have the output layer, O. And the parameters that are in between them are similar to single layer MLP. We are going to have a W matrices. So for example, WO here is from the input, or W0 basically here is from the input layer to the first hidden layer, and B0 is the bias vector for that. And then we have W1 here and B1, W2, B2, etc., until we have WH minus 1 to be also BH minus 1, and finally we have WH and BH. These are the parameters of the model. And out of all of these, if we are given an input X, we can actually calculate the output O using this network, and having the output O and using the actual outputs that are in the data, Y, we can calculate the error or epsilon of X. So you can see that it's very similar to what we have seen before. So the input layer, it has D+1 dimension of neurons, and then for each of the hidden layers we are going to have different number of neurons. We are going to decide on that when we are designing this architecture. So for example, this is going to have M1, I just drop plus ones, you already know that, right? M2 until MH, different neurons in these layers that are hidden layers. Additionally, you remember that when we were calculating output of each layer, what we have done was that first we calculated a net value, and then we applied the activation function on that net value that usually was a nonlinear, like a sigmoid or tanh function, right? So here also we are going to have similar functions. So for example, for the first layer, we are going to have F1, that is the activation function for first layer, F2, activation function for the second layer, until FH, the activation function for the last hidden layer. These activation functions are not necessarily the same. They can be the same, but also they can be different. When we also decide this when we are designing the architecture. Okay, so this way we can actually number the layers that we have, right? This is layer 0, this is layer 1, 2, until we have layer H, and then it's the output layer, or H plus 1, or output layer. So when we have Wi, it's basically the weight matrix between layers I and I plus 1. And then when we have BI, it's the also weight vector for bias between layers I and I plus 1. And so when we are having a feed-forward situation, when we want to calculate the output given an input, what we have is very similar to what we had before in the single-layer perceptron. So, single-layer MLP. So our output is going to be the activation function for the output layer applied to the net that is coming from the previous layer, right? So what is that net? It's basically WH transpose ZH, right? So ZH is coming from the previous layer. So we calculate WH transpose ZH plus BH, right? And that is going to be the output of our output layer. Now, if we decompose ZH, we know that this ZH is actually equal to, so we still have FH plus 1. We just decompose WH, ZH, and ZH is calculated according to its own previous layer, right? So basically, I can write BH on this side to make it easier. It's going to be BH plus WH transpose. Now, instead of ZH, I can rewrite ZH as BH minus 1 plus WH minus 1 transpose ZH minus 1, right? Okay. And again, I can rewrite ZH minus 1 according to ZH minus 2, right? So it will be F of H plus 1 BH plus WH transpose BH minus 1 plus WH minus 1 transpose. And now I can rewrite ZH minus 1 as BH minus 2 plus WH minus 2 transpose ZH minus 2. So you can see that easily we can go and expand this kind of formulation until we get to the first input layer. So we can rewrite this whole output according to the input layer. And that is going to be FH plus 1 of BH plus WH transpose BH minus 1 plus WH minus 1 transpose. Oh, I dropped the F, so we have actually F here. Sorry about that. So we do have an activation function for each of these. So there is an FH here, and there is an FH minus 1 here, right? Okay, so multiplied by FH minus 1, etc., etc. And then finally, we get to the first layer. So it's F activation function for the first layer, B0 plus W0 transpose X, which is our input, right? Okay, so basically this is the feed forward part of the network. So when we want to calculate our output according to an input, so when we are given an input and we know the W's, we know the B's, and we know the activation functions, we can just calculate all the output for that input like this by applying all of these, by calculating the nets in each layer, applying the activation function on top of that, and moving forward. So this is the feed forward phase. And you remember that we had a feed backward phase also. And that was when we wanted to back propagate the error backwards in the network so that we could learn the W's and the B's, like all of the parameters that we had in the model. So when we had this error, what we did in single layer MLP was that we backpropagated it. So we calculated these net gradients for each of the layers, and we updated the parameters W's and B's according to those net gradients. So what we had was that we had these backward propagations of the error, and we calculated a net gradient for each of these layers that we had. So at the beginning, we had the net gradient delta O from the output layer, it went back, and then we have delta H, etc., until we have delta 2 and delta 1. These are the net gradients that we calculate at each layer, and using them, we can update the values of parameters W and B. Okay, so let's just catch up and remember what we did there. So what we had for the output layer, delta O for output layer, which is assuming that we have independent outputs, meaning that the O1 doesn't depend on O2, doesn't depend on O3, etc., etc. For example, when we are using a sigmoid function in the output layer, then we are having this independence assumption. If we do use a dependence kind of function, activation function, like the softmax, then it's a little bit different, but I'm going to tell you how different. So in softmax, you remember that we normalized the values that we had for probabilities by dividing the values over sum of all other outputs. So the value for one output, the final probability was the value for the output divided by summing over the values for all other outputs. That's why the outputs are not independent if we are using softmax. But suppose that we are using something like sigmoid. So for the output layer, when we have independence in the outputs, so delta O, which is basically delta H plus 1, what is it? This is the derivative of, partial derivative of output activation, element-wise product with the partial derivative of our error, right? Which is basically what we are saying is that the derivative of error with respect to net O, so the net for the output, the net value for the output layer, we can write that using the chain rule as the derivative of error with respect to the output itself, or activation f of O over net, multiplied by the derivative of, so this is, I can rewrite it like this so that it's easier, maybe FO of net O, multiplied by the derivative of FO of net O over the net O itself, right? So basically, this is the chain rule that we have. So also we know that FO of net O is the output itself, right? The vector of output. Okay. So if the outputs are independent from each other, the FO over net O, the derivative of FO of net O is going to be a vector if outputs are independent. But if they are depending on each other, it's going to be a matrix. So matrix if outputs are dependent. And the matrix that we are going to have, it's going to look like this. It's going to be a matrix, let's call it F, which is, it has all the partial derivatives in it. So it's going to be the derivative of O1 with respect to net O1. O1 is basically FO of net O1, right? And the derivative of O1 with respect to net O2, etc., derivative of O1 with respect to net OP, because we have P outputs. Continuing here, also the derivative of OP with respect to net OP, etc., and the derivative of OP with respect to net OP. So if the values are, the output values are dependent on each other, we have, we can have a derivative of, for example, O1 with respect to net OP because they depend on each other. In the formula of O1, we have net OP, right? But if they are independent of each other, if you look at this matrix, all these little derivatives are going to be 0, except the ones that are on the diagonal. That is the derivative of OI over net OI. And that's why it can be represented by just a vector, because it's basically a p-dimensional vector, right? So this is for the outputs layer. And for all other layers, what we are going to have is like this. We are going to have delta I is going to be, again, we can write that as the derivative of Fi, which is the activation function in that layer, and element-wise product of wi dot delta I plus 1. Now you remember that we have that in one layer MLP also. So the derivative that we had for our delta for the hidden layer was basically the derivative of the activation function element-wise product with the wi dot the delta of the output layer. And the reason was that we talked about it. The reason was that we said the error when it is back propagating, when it is going back to a layer before, it is weighted by the weights that are connecting to the neuron that we are talking about. So it is basically the contribution of error is going to be affected by all of these weights when we are going back. So if we want to look at it in MLP with more layers, it's going to have a similar format. So we're going to have the derivative of activation function, element-wise, a weighted contribution of error when we are back propagating from the layer that is in front of us. This is actually something that is very generic. It can be used in all different kinds of setups. Like we are going to have a similar formulation in backpropagation for many, many networks. And then now we wanted to also update the parameters, right? The goal of calculating all of these net gradients was to be able to update the values of parameters, right? To be able to calculate the gradients of wi's so that we could update the wi's. So the gradient of wi is going to be equal to zi dot delta I plus 1 transpose. Okay, this is also very similar to what we had in single layer MLP, right? Okay, and basically, this is what you need to know, all of this, for learning the W's. Now, what we can do is that we can actually do this backpropagation and gradient calculation in a generic format so that you can see how we get there, right? For example, for the output layer, so calculating backpropagation gradients. So for example, for the output layer, we have a neuron that is like OJ from all of the output layers that is equal to FO of net OJ, right? Net is calculated for this specific neuron OJ, and F is going to be applied to that, and that's going to give us our output. And net OJ is BJ plus summation of W AJ ZA. A is equal to 1 to M. Now, we know that the gradient of error, so the gradient with respect to one Wij, one parameter, is what? It's the gradient of error with respect to Wij, right? Which what we are going to do is that, so it's the gradient of error, depending on what error is, over this Wij that we have in net Oj. So what we can do is that we can rewrite this as gradient of error with respect to net Oj multiplied by gradient of net Oj over gradient with respect to Wij. right? This is the chain rule that is going to be used for all the calculations, all the gradient calculations in deep learning, because that's the standard we are going to do. It's going to make things much easier. And you remember that this is what we called the net gradient delta OJ, right? So this part, the delta OJ, it depends on the error formulation. It depends on what function, what loss function you're using for your error. The derivative of net OJ with respect to Wij is basically this one, the derivative of net OJ with respect to Wij. It's the net OJ that we have there, right? The derivative of Bj plus sigma Waj Za A equals to 1 to M over with respect to Wij, right? Which is basically going to be Zi, right? Now, the derivative of the green part, the delta OJ, it depends on what the formulation for error is. So assuming that our error is the squared loss, which is 1/2 over norm of y minus o squared, it's actually 1/2 of sigma I equals to 1 to p yi minus oi squared, right? So we can easily take the derivative of, we can easily calculate delta OJ, which is the derivative of error with respect to net OJ, right? And that we can again use the chain rule. We can say, okay, it's equivalent of the derivative of error with respect to OJ itself multiplied by the derivative of OJ with respect to net OJ. Why are we doing this? It's just easier to do it because you can see that in the error function definition, we do have O in it directly. So it's just easier to take the derivative of that with respect to O and then take the derivative of O with respect to net OJ. It's make things simpler. Now, this part, the derivative of error with respect to OJ, it depends on the formulation of error, right? It depends on how O is used in this error. And it is basically, according to this, and if you take the derivative, I'm sure you can do that at home, it's going to be equal to Yj minus OJ, right? And the second part, the derivative of OJ with respect to net OJ, this one, it depends on the activation function, right? Because OJ is, we know that OJ is F of that layer, FO of net OJ. So depending on the activation function, it's going to be different. So assuming that our activation function is, for example, sigmoid, so if FO is theta of net OJ, or sigmoid, the sigmoid function is usually represented by like sigmoid, but because we do have other norm, we are using sigma for variance and all, we have tried to use theta in the course. So anyways, so if our F is a sigmoid, we know that the derivative of sigmoid with respect to its parameter is going to be the parameter, sigmoid of the parameter itself multiplied by 1 minus sigmoid of the parameter Yes, so it's going to be basically OJ, which is sigmoid of the parameter itself, multiplied by 1 minus OJ, which is the sigmoid of parameter. Okay. So basically, we calculated the net gradient using the squared error and the sigmoid activation function. We also calculated this derivative of net OJ with respect to Wij. So from here, and using 1 and 2, we can see that derivative with respect to Wij is Zi Yj minus Oj, Oj 1 minus Oj. All right. And we writing it in the vector form, we get to what we have seen before. So in the vector form of it, if you remember, we had this one. So if I have a vector form for this, it's going to be O minus Y vector form, element-wise product with O vector, element-wise product with 1 minus O vector. And well, the vector form of Zi, if you put all the Zi's together, it's going to just be Z, right? And the vector form of the gradient is going to be the derivative with respect to, it's going to be a matrix now, right? Because we have a matrix of W varying I's and J's all. So we are going to have WO because we're looking at the output layer. It's going to be Z multiplied by O minus Y dot inner element-wise product O, element-wise product 1 minus O, which is actually this one is also a vector, right? Or in other words, we can say that the gradient WO is all the Zi's and net gradients of OJ's for all I and J's that are in our data, or we can say it's equal to vector Z dot delta O vector transpose. Okay, so for the hidden layers, we also have a similar situation. We calculated that for hidden layer of MLP, and basically the generic formulation is going to look like this. We are going to calculate the gradient of Wij, and that is going to be equal to the gradient of our error with respect to Wij. That is basically coming from a hidden layer like H, for example. So that is going to be equal to the gradient of error with respect to net of Zj, right? So the net of the layer Zj that is for that hidden layer multiplied by the gradient of net Zj with respect to Wij. So again, similarly, we are going to use the chain rule. Now, this first thing, the gradient of error with respect to net Zj, you remember that we defined that as delta Zj, which is our net gradient, right? And then basically this is going to be the net zj with respect to wij is basically going to be xi, because we know that our net zj, when we have just one layer, we know that our net zj is going to be a combination of wij's multiplied by x's, right? But when we have different layers, then this is not going to be x anymore. This is going to be the input to the layer that we have, right? So that is going to be zi now, right? So if I want to actually write that, it's going to look like this. We are going to have, for multiple layers, we are going to have the derivative with respect to the derivative of all parameters in layer L of hidden layers is going to be equal to ZL, the output of our layer, dot the net gradient of the next layer, L plus 1 transpose. So this is also a generic formulation. So this is the output of layer, and this is net gradient of next layer. Okay. Now, to calculate the net gradient, so this is the net gradient that we have here. To calculate the net gradients, we also had this formulation that we said that the net gradient for zj, for example, is the derivative of error with respect to net zj, right? And that depended on it was basically a combination of the weights that built our ZJ and then with the nets that we had, right? So basically we can rewrite that as, because there are p different, if we are, for example, in one layer, there are p different weights that are making our net ZJ for us if we are in one layer. So for one layer, we had k equals to 1 to p, the derivative of epsilon with respect to net OK, multiplied by derivative of net OK with respect to zj, multiplied by derivative of zj with respect to net zj. Why? Because remember that we had these output layers, O1, O2, until OP, right? And we have this ZJ here, right? And the way that they were connected to ZJ were with these weights, right? So we had all of these W's, W1, W2, for example, WP, right? J, J, and J. And basically what you are doing, you are trying to look at the gradient of error, that is as a comparison with all the O's with all the Y's. You want to calculate the gradient of error with respect to net ZJ, right? So net ZJ is here right before the activation function for this layer. So we have this calculation of W something something, X something something for ZJ, and then we apply the activation on top of that, right? Now, so we are calculating the derivative of this with respect to this. And what we are going through is that we are going through O's, we are going through W's, we are going through F to get to the value of net CJ. So that's what we are doing here. So this is as if we are going, we are taking the derivative of error with respect to the net values in this layer. Then we take the derivative of the net values with respect to zj here, which is basically f of this net zj. And then we take the derivative of this zj, which is f of net zj, with respect to net zj itself. So we are doing it in step by step, and then we are summing over all these routes that we are going. So once we are going through O1, once we are going through O2, etc., etc. Okay, so basically having that, we said if we rewrite this in a vector form, we have the net gradient for a hidden layer, a specific hidden layer, which is basically net gradient of Z1, net gradient Z2, etc., until net gradient of Zm, the mth neuron in that layer, is going to be equal to the derivative of fh for that layer and element-wise product with now, well, if we have multiple layers, we are going to have use indices, but if we have only one layer, it's going to be WO delta O. So this is for one hidden layer. If we have multiple hidden layers, like similar to here that, well, we calculated for one hidden layer and then for multiple. If you have multiple hidden layers, what we are going to have is that the net gradient for layer L is going to be the gradient of activation function there, FL, element-wise product of WL dot the net gradient for the next layer, as it is, it's as if the net gradient for the next layer is propagating to this layer weighted by these WLs, right? And then we have the dot product with gradient of F. So in general, if we have multiple layers, so when we have many layers, the formulation that we have for the updates are like that. The derivative with respect to WL is equal to ZL dot net gradient for L plus 1 transpose. The derivative with respect to BL is similar. It's basically the net gradient for L plus 1 layer, because the Z for the bias is always 1, right? So it's going to be equal to net gradient of L plus 1. And for the output layer, things are a little bit different. The net gradient for output layer is the gradient of FO, element-wise product, gradient of R, and the net gradient for else layer is gradient of FL, element-wise product with weight of that layer dot net gradient of L plus 1. Right. So using these, we can basically have a generic MLP and learn an MLP that has multiple layers, hidden layers, more than one hidden layer. So when we are training, the algorithm is like that. As an input, we are going to have D, our data. We are going to have H, how many hidden layers we are going to have, and nu, which is basically the step size. Max iter is the maximum number of iterations we want to go over the data. And then we have these specifications for the layers, right? Number of neurons for each of the layers and the activation functions for each of the layers and the output layer. So what we do, we start by initializing the weight matrices and the bias vectors. We initialize all the parameters with small random values. And then we keep an iteration counter. And we are going to repeat max number of iterations. So we are going to have max iter number of epochs going over all data. And for inside each of these iterations or epochs, what we are doing is that we randomly select one data point from our data set. And using the feed forward phase, we are going to calculate the z's and the output for that data point. Then we are going to calculate the net gradients for the output layer. If we have a sigmoid function for the activation function, which is going to give us independent outputs, we are going to have a vector for gradient of h plus 1. Otherwise, we are going to have this matrix. And then after we calculated the net gradient for the output layer, we are going to calculate all of the net gradients for previous layers, because we have seen that the net gradients in each layer, they depend on the net gradient of the next layer that we have, right? So when we have the net gradient of output, we can calculate the net gradient of the layer before, etc., etc. So we go back. And then after we have calculated all of those, then we are going to update our parameters or W's. Now going from the layer 0 to the last layer, we are going to update the gradient of W for that layer by multiplying the Z of that layer with the net gradient of the next layer transpose. Similarly for the bias vectors. And after we calculated all the gradients for the parameters, gradients for W's and B's, then we are going to do the gradient descent step. And we are going to update all of the parameters by moving in the opposite direction of the gradient so that we can find the minimum values. So this is multi-layer perceptron when we have multiple layers. Hello everyone, this is Sherry Sahibi, and we are in the data mining class. So I'm going to talk about a problem that is vanishing or exploding gradients in deep network. So in deep network, when we have multiple hidden layers, as we have more and more layers, when we are calculating the gradients of these layers, we are taking the error and propagating it backwards towards the beginning, right? To calculate all the parameters, W's and B's. Now, as we move towards the beginning, the gradients that we are calculating are either going to get too small or are going to get too large. So when the gradients get too small, that it leads to no change in the values for the parameters. So if the gradient is getting too small, it means that when we are trying to update the value of a parameter in our stochastic gradient descent iterations, because the gradient is too small, the parameter values are not going to change. So we are going to see no change or very, very slight changes in the parameter values. And basically, we are not going to learn much for those parameters. That is called the vanishing gradient problem. On the other hand, there is another problem that can happen, and that is as we are propagating our errors backwards towards the beginning of the network, the gradients are going to get too large. And when they get too large, then basically we are going to grow our gradients exponentially with the layers. And it's going to make our network to not to learn the correct parameters for the model. So why is this happening? For example, you remember that when we were talking about multi-layer perceptron, our gradients are going to be updated like this. We had these net gradients, for example, that the net gradient for layer L, so the net gradient why does this happen? We know that the gradients depend on each other. The net gradients depend on each other when we are back propagating them. For example, in multi-layer perceptron, what we had for the net gradient of layer L was like this. The net gradient for layer L was the derivative of f of activation function for that layer, element-wise product with the parameter matrices of that layer dot the net gradient for the next layer, L plus 1. Now, if I replace L plus 1 with a similar formulation, I'm going to have the gradient of FL dot W. Now, I can rewrite delta L plus 1 like this. It's going to be the gradient of FL plus 1 dot WL plus 1, L plus 2. And I can rewrite this and go forward, right? Now assume that, for example, in a very simple case, when our activation function is just a linear activation function. In that case, the gradient of f is going to be 1, right? And it's just for simplification that we are assuming that. Then if gradient of f is 1, we get to this formulation that net gradient for layer L is going to be equal to WL multiplied by WL plus 1 multiplied by WL plus 2, because we are expanding all of these deltas, right? For each of the layers, we are expanding all the net gradients multiplied by L multiplied by WH plus 1, for example, if you have H layers. Then what happens is that, and eventually, actually error fx. So what happens if that is that if these W's, the matrices that we are multiplying the error with, as we are back propagating to calculate the net gradient of layer L, if these W's are somehow in each multiplication make the value of error smaller and smaller, as we go backwards, our error value is going to get smaller and smaller, and we are going to have this vanishing gradient problem that our net gradient at some point is going to be close to 0. On the other hand, if our W's are set in a way that they are kind of large, and in every multiplication they make the value that they had larger and larger, eventually when we get to the beginning of network, our net gradient is going to be too large. So these are two problems that we have when we have deep networks. Now, what kind of W is going to make things larger and larger, and what kind of W is going to make them smaller and smaller? You know that we can have an eigen decomposition for W's, right? So if I have WH, I can rewrite it as U delta U transpose, or U minus 1, that U's are eigenvectors and basically normal eigenvectors, and delta is a matrix of eigenvalues, delta lambda 1, lambda 2, until lambda m. for example, and these are zeros, right? Now, if our W is set in a way that the value for lambda 1 is larger than 1, when we multiply our W again and again, we are going to have an explosion happen. And when our lambda 1 for all the matrices that we are multiplying is going to be less than 1, then we are going to see a gradient vanishing problem. So only when lambda 1s are kind of close to 1, we are going to be okay with that, right? So what do people do to fix this problem, to avoid this problem, is that whenever we have the gradient explosion, meaning that our gradients are getting larger and larger, one simple way to avoid it is to have a cap on the gradient. It is called gradient thresholding, meaning that if our gradient is getting larger than a specific threshold value, and we set that value, then we are going to just reset the gradient to that value. So we set the gradient to the maximum value that we allow, even if it's larger than that value. So that's one way to deal with gradient threshold, gradient explosion problem. One other way to deal with this problem is to add regularization to the W's. So you remember from regression that we added lasso, for example, regularization to have W's in a certain way. We wanted to have W's to be small, the norm of W to be small. So using the regularization, we can impose some kind of constraints such that this lambdas, the eigenvalues of our W's to be close to 1. So that's another way to solve this problem. Another way to solve the problem of vanishing gradients is to use different kinds of activation functions. So in vanishing gradients, one of the problems that happen is that if our f, this function, is the activation function is a kind of activation function that its gradient is 0 in a lot of times, then when we multiply the gradient of f with everything that is in front of it, we are going to get zeros, right? So it makes our gradient small and close to 0. So for example, when we have sigmoid activation function, the sigmoid activation function is 0. The gradient of it is 0 in many places, right, that are not close to 0. So whenever we are close to 0, the gradient of sigmoid is non-zero. But whenever we go farther from 0, the gradient at the two ends are going to be close to 0, or it's going to be too small, basically, here, to have a good effect. So it's going to really make our gradient smaller and smaller. So to avoid this kind of gradient vanishing problem, what people do is that they don't use functions like sigmoid functions as the activation function. Instead, they use activation functions like ReLU or tanh that their value of the activation function, the gradient of activation function is not always or most of the time 0. Okay, so that's one way to address this problem also. Usually people use sigmoids mostly in the output layer, and in the middle layers, because of these problems, they use other kinds of activation function. So these are basically the gradient vanishing and explosion problems in deep neural networks. Hello, this is Sherry Sahabi, data mining class. We are going to talk about recurrent neural networks, or RNNs. RNNs are a type of deep networks that are used for sequential or temporal data. So for example, if your data has some kind of time dependency between the data points, or it is coming from a sequence, then RNNs are a good option to model your data. What are some examples of those? For example, suppose that you are working with the stock market and the price of a stock, it not only depends on what is going on right now in the world, but also it depends on the previous price of this stock. Or suppose that we are working with textual data. In textual data, suppose that we are trying to translate a sentence from Spanish to English. Now, in your text or in your sentence, the order of words matter. So your sentence is basically the sentence is a sequence of words, right? So what we can say is that, for example, the words that you see in a sentence, the word that you see at this part of the sentence, it depends on what words have been coming into the sentence before that word, right? So basically your words depend on the choice of your next word depends on the words that you have said so far. That's some kind of a sequence situation in your data. So basically, the structure of RNNs are set up in a way that they can capture this sequential information or this dependency between the data points that we are seeing. Because the data points are not independent in a sequence, they depend on each other. So our RNNs, they do have the input layer and the hidden layer and the output layer, similar to multi-layer perceptrons, and the feed forward also between these layers. But in addition to that, they have this feedback loop that we put a -1 here to show that this hidden layer, each hidden layer at each time depends on the previous value of that hidden layer. So basically, it means that the output of hidden layer Z feeds back into the next time that we are calculating the value of Z. Z not only depends on your input layer X, but also it depends on its own previous value. Previous is shown by -1 here. So what we can think of is it's like a hidden state for our data. For example, suppose that you are having sentences as your sequences, right? And each word, it depends on what you want to say at this time. And basically that thing that you want to say at this time is summarized by a hidden state at the previous time that you had this sentence. So the sentence so far plus what you want to say at this time, right? Okay, so if that's the case, then what is your input? If you have the sequences, what is the input that you are going to have? So your input data, your whole data set, is going to be a set of sequences. Okay. For example, in the case of text, it's going to be a set of documents. Each document is a sequence, right? So instead of a set of vectors that we had so far, like in regression, we are having a set of sequences. So D is a set of sequences xi. How does xi look like? Xi is like this. It's xi1 vector of xi1, vector of xi2, until vector of xit. What does xi1, 2, and t mean? Each xij that we have is the jth input vector for the ith sequence. Okay. So, for example, what you can think of is that each of your documents, so your whole data is a set of documents. And each of the documents that you have is one sequence, a sequence of words, right? And punctuations, for example. So each document is a sequence of words and punctuations. And as a result, each xi is one word or one punctuation. And T is the length of your document, how many words and punctuations are in it. Okay? Let's give an example of that. So suppose that you are having like a sequence of genes, right? And you have three alphabets to show the sequence of genes in your data. Now, your alphabets are G, D, and A. Okay, and your sequences are like this. You have sequence X1, which is GGDA. You have sequence X2, which is DGA. And you have sequence X3, which is AGD. Okay? All of this is your data. Each sequence is going to be basically one of, like each of these are going to be one of your sequences. And then inside the sequence, we are going to represent these sequences in a way that our algorithm understands, right? And you remember that the data representation, when we had categorical data, we could represent them with binary vectors, right? So for example, right now we have 3 letters and we can represent them with a binary vector of length 3. We can say G is the vector 1, 0, 0. D is vector 0, 1, 0. And A is vector 0, 0, 1. Right? So I can represent my x1 like this. I can say that my x1 is this. I have G in the first one. So it's 1, 0, 0. G in the second one, 1, 0, 0. D, it's 0, 1, 0. A, 0, 0, 1, right? So I have a vector of length and the sequence of length 4. So this is the length of my sequence. And each element in the sequence is a 3-dimensional vector, like a d-dimensional vector. Now, for example, x3 is like this. The first one is A, so it's 0, 0, 1. The second one is G, it's 1, 0, 0. Last one is D, it's 0, 1, 0. So that's how we encode our sequences in our data. Our data can be also labeled, right? So for example, in case of translation, now suppose that we want to translate these gene sequences into some other kind of sequence. And suppose that this new sequence, its alphabet is now different. It's alpha, beta, and gamma. So for each of these X's, we also have a Y. So we have a sequence Y. So we have Y1, we have Y2, and we have Y3. These are our response variable or target variable. And we are trying to match our input data to this output data. So for example, for sequence 1, suppose that it is beta, beta, gamma, alpha. And for sequence 2, it's gamma, beta, alpha. And for sequence 3, it is alpha, and G is the next one, beta, gamma, right? So similarly, what we can do is that we can encode, like these are going to be encoded into their own version of sequence. And our whole data is going to be similar to the classifiers that we had, for example, is going to be pairs of input and response. So pairs of sequences, x1, y1, x2, y2, x3, y3, etc., etc. So this is our D. All right. So this is an example of what sequential data may look like and what kind of task we want to do with this kind of sequential data. Usually for these kinds of networks, we consider a specific length, maximum length for the sequences, max length of sequences, and we use tau for that maximum length of sequence. If a sequence is shorter than this, for example, if our tau is 4 and well, x2 is shorter than 4, what we can do is that we can pad this sequence with a specific character unknown, for example, so that all of the sequences that we have in the data set are of the same length. Right? So basically this tau is going to be the same for all the sequences in our data. Okay, so we talked about the structure. Now, because we have these time dependencies or a notion of time in the sequence, we have to adopt this structure to also have a notion of time, right? So as a result, in the structure of RNNs, what we are going to have is that we are going to have xt in our input, which is basically our input at time t, and t can be from 1 to tau. We have zt, which is our hidden state at time t. And also we have our ot, which is our output at t. Okay, so for example, we can have our x1 like this. This is our x1, 1, because it's from x1 at time t. This is x1, 2, vector x1, 2. This is x1, 3, x1, 4, right? And then similarly for the outputs, we have O1, 2, O1, 3, or Y1, 2, Y1, 2, 3, etc. Right? Similar to multi-layer perceptrons, we have d dimensions, right? So this is d dimensional x, like here, that we have 3-dimensional x here. We have m dimensional z's, and we have p-dimensional output layers. Okay, and we are going to feed the x's, each x at each time, one by one to the network. So we feed xi1, then we feed xi2, then xi3, etc., etc. Now, what are the parameters that we have? Similar to MLP, we have these parameters of, for example, this is the W input to hidden layer at time t, and this is B of bias vector of hidden layer at time t. And this is the W of hidden to output layer at time t, and this is B of output layer at time t. In addition to those, you remember that we had this feedback loop, right? So we need some parameters for the feedback loop also, and that is WH between hidden layer and hidden layer at time t, and B between hidden layer and hidden layer at time t. For each layer, we only need one bias parameter vector. So we can just basically get rid of one of them. So I can just get rid of this one for this layer and just keep this vector. Okay, so basically the parameters of the network are WIH at time t, WHO at time t, and WHH at time t, right? This is a D by M matrix. This is a M by P matrix, and this one is an M by M matrix. Also, we have the biases, right? So we have this, we have this, we have the biases. So it's BHO at time t and BH at time t. And these are the vectors. So we can have these parameters for each time, each sequence time, we can have a different set of parameters. So how many parameters are we going to have? If the length of parameter is tau, the maximum length of parameter is tau, then how many parameters should we learn? Well, we have to learn tau of WIHs, so D multiplied by M, plus we have to learn all the values in the matrix WHO also, so M by P plus M by M plus P plus M for BH and BHO, right? So that is lots of parameters. This is too many parameters, especially if your sequences are long. If your tau is large, then it's going to be too many parameters. So what we do is that in RNNs, we just say that although we have different times of the sequence, we assume that the parameters are the same during all of these times. So what we do is that we are going to set all weights or all parameters for all times to be equal to each other. Basically, we are going to get rid of subscript T. We are saying WIH at time 1 is equal to WIH at time 2, etc., etc. So basically, the parameters that we are going to be left with is just going to be WIH matrix, WHH matrix, WHO matrix, BH vector, and BO vector. Okay, so this is the set of parameters that we are going to have for RNN when we have the structure that you see above. Now, how are we going to calculate the output? What is the feed forward, like similar to feed forward calculations for RNN, because, well, it's we said that it has this feedback loop. So how do we calculate the output? So first of all, we said that the value of Zi at time t, it depends on both the value of input, so it's a function of both the input xit and the value of Z at time t minus 1. So Zi and t minus 1, right? That's what was our assumptions. That's what the feedback loop is, right? So just for simplicity, we are going to drop the I, and we are going to, for simplicity, we are going to say, we are going to rewrite it like that. Z at time t is equal to a function of x at time t and Z at time t minus 1. Okay, so how are we going to calculate the net for our hidden state at time t? What is the forward pass that we are going to have? So to calculate the output, first we are going to calculate the net of ZT. Okay, so what is net of ZT? it is equal to, now, because it's a function of both x and z, so let's first do the x thing. This is similar to MLP. It's WIH transpose XT plus BH. This is similar to MLP, right? But also it depends on ZT minus 1. So with the set of parameters that is in WHH, right? So matrix WHH transpose Z of T minus 1. So this is the value of net ZT for us. In the next step, we are going to apply activation on net Z, right? So how are we going to do that? We are going to say ZT is equal to the activation FH over net ZT. And this activation is basically, it's going to be applied element-wise on the vector of net ZT. The vector of net ZT, it includes all the net values for Z1, Z2 until Zm. Like if this is a vector of Z1, Z2, Zm, then net is net Z1, net Z2 until net Zm for that hidden layer. Okay, what is the next step? Third step. Well, we have calculated the hidden layers value. So we are going to move to the output layer and calculate the net for OT, which is equal to, this is totally the same as MLP's, it's WHO transpose ZT plus BO. And finally, we are going to apply activation over the net O. So we are going to calculate the output OT as FO of net OT. This is also the same, similar to MLP. Okay. And so this is the forward pass. Now for the backward pass, again, we are going to, so this is forward. For the backward, similar to before, we are going to calculate the error and then propagate it back in time. So for example, suppose that our error is the squared loss. So we are going to have, now because each of our data points is a sequence, we are going to calculate the error for each of the elements of this sequence. So the error is going to be equal to, from time equals to 1 to tau, the error for xt, which is basically equal to t equals to 1 to tau, 1 over 2 squared error, yt vector minus ot vector norm. Okay. Now it's time to back propagate the error to the previous layers, and so that we can calculate the values, the gradients of W, and also update the values of the parameters. How are we going to do that? The way that we are going to do that is by unrolling or unfolding the sequence structure or architecture in time. So what we are going to do is that, you remember that we had this architecture with a loop in it. So we are going to open up the loop and we will end up with this kind of architecture. So we have this input layer here. So H0 is basically the same as our x. And then we have hidden layer H1, which is basically similar to Z1 here. So it's like Z at time 1. So Z1, and then H2, which is Z2, until we have H tau or Z tau. Okay. And then, oh, sorry, this is not X, this is HO. For each of the Z's, we have also one input, right? So our sequence of input X's are here. So X1, X2, until X tau are here. They are going to feed into our Z's or H's. And these are with WI. All of the WI's are the same. And also, we are going to have the output layer from time 1 to time tau. And we are going to have WOs as the parameters. In addition to that, between each two hidden layer, we have the WH and BH. So this is the feedback loop that is unfolding in this way. Okay. So having this, we can calculate the net gradients easier, and we can actually see what the gradient values are, right? So basically what we have is that we have Zi or Hi is equal to Fh of WIH transpose X plus BH plus WHH. Actually, let's do Z1. So that is easier. Z1. So this is X1 and WHH transpose Z0, right? This is, for example, Z1. And then we can have Z2 like that, Z3 like that, etc., etc. Now, how to train? We have to calculate the net gradients, right? So to do that, what we do is that, similar to MLP, we are going to first reverse all the edges. So these are the edges that we are going to back propagate with, right? And then we are going to start from like this first one in this back propagation way, so which is going to be the output layer. We're going to start at the last layer, which is our output layer. And we are going to compute the net gradients and go backward. So we compute the net gradient here, and then we go backward, we compute the net gradient here. We start here. So net gradient calculations, net gradient here, here, there, etc., etc. And after we calculated the net gradients at all the hidden layers and everything, then we are going to compute the gradients for all the parameters and do the gradient step. Okay. So how can we calculate the net gradients? So the net gradients for the output layer is similar to MLP. So delta OT is derivative of FO, element-wise product derivative of error with respect to OT. Okay, that's basically the same because we don't have any feedback loop in the output layer. But to calculate the net gradient for other layers, we have to do it in a reverse order. So we are going to start with tau and go to tau minus 1, to tau minus 2, etc., until 1. And we are going to calculate net gradient for layer tau first, and then layer tau minus 1 until the first layer. So for the layer tau, the net gradient is going to be similarly the derivative of fh, element-wise product. Now, similar to MLP, that when we wanted to backpropagate the net gradients, we weighted it with our W's. We have a similar situation. So this is going to be element-wise product with WHO and net gradient of O tau. Okay, so like here, oops. So here, for this one, for specifically the last hidden Z that we have, or the last hidden H that we have, nothing is feeding into it from any, we don't have any further hidden H's, right? So whatever that is coming to this layer is coming from O. That's why we only need to calculate the net gradient of O and backpropagate it into this hidden layer using the weights WO. This is only for the last layer. Okay, so for the last layer, we have this kind of net gradient. But then if we look at H tau minus 1, we can see that the error is backpropagating into it from two ways. One is from O of tau minus 1, and another way from H tau itself, right? So basically, if you actually calculate that, but also we can guess it, the net gradient for tau minus 1 is going to be the derivative of activation function, element-wise product. Now, this is going to be, first of all, the WHO and then the net gradient of O tau minus 1. This is similar to net gradient for tau, but also something is coming to this node through the the net gradient of the previous layer also, right? So it's going to be WHH from the previous layer of Z tau. We get WHH net gradient of Z tau here, right? So this is basically the same as propagating the gradient from H tau or Z tau to H tau minus 1. So it's the, basically what you see here is the weighted sum. So this is a weighted sum from the output layer and the previous layer Z tau. So for tau minus 2, the net gradient is going to be FH O WHO net gradient of O tau minus 2 plus WHH net gradient of Z tau minus 1, etc., etc. So this is how we are going to backpropagate the error using the net gradients. Now, okay, we have calculated the net gradients. Now we have to calculate the gradients of the parameters themselves, right? Everything that we are doing is to be able to take the gradient with respect to, for example, WHH, to be able to update the values of WHH, right? What is that? That is the derivative of epsilon, or the error, with respect to WHH. Similar to MLP, we are just going to use the chain rule, and because this is of a sequence, we are going over all the times in the sequence, so t equals to 1 to tau, and that is going to be equal to z t minus 1 dot net gradient of zt transpose. Okay. If you calculate that, you will get to this. I'm just summarizing so that we don't go into that much of a detail here. And for WHO, it's going to be the summation of t equals to 1 to tau zt net gradient of OT transpose. For BO, you can see the similarities between this and MLP, right? It's the summation of t equals to 1 to tau net gradient of OT. And for BH, it's the summation of t equals to 1 to tau net gradient of ZT. And finally, for WIH, it's a summation of I equals to 1 to tau xt delta net gradient for ZT transpose. After we have calculated all of these gradients, then we are going to do the gradient descent. So we are going to, for example, set WHH is equal to WHH minus step size gradient of WHH. We are going to do that for all the parameters. So that is how we train the recurrent neural networks. Okay. So there is one problem in RNNs that if our tau is too large, for example, if we have a long sequence, in the back propagation, we get the gradient explosion problems. For example, the net gradients are going to go to infinity, or sometimes maybe we have the vanishing gradient problem. So the net gradients are going to go to 0 as we are back propagating. And the reason is that when we are calculating the net gradients for example, HT, it depends on WH, and then it is calculated according to the net gradient of the previous time multiplied by the previous time, etc., etc. So you see that the net gradients, they depend on each other. So we are going to get this vanishing or explosion problem. And one of the things that we can do to solve that is to regularize the parameters so that, for example, keeping the spectral radius of these parameters to be close to 1 so that we don't get to this vanishing or explosion of gradient problem. Hello everyone, this is Sherry Sahebi, data mining class, and we are going to talk about long short-term memory networks, or LSTMs. So LSTMs are being created to solve the problem of vanishing gradient problem, or the explosion in gradients that can happen by going deeper and deeper in deep networks. So in LSTM, what we have is that we have an additional gate layer that is differentiable, and it can resolve the vanishing gradient problem. It also has a nice interpretation. So what is that gate layer? in recurrent neural networks or RNNs, you remember that we had this hidden layer that kind of could have been working as a memory. So in LSTMs, what we have is a selective read and write operation, and we store some of the values in the memory and forget some other values of the memory. So for example, what we have is that, suppose that we have a vector of values like 0.2, 0.7, and 0.1. Now, if I do a simple operation of element-wise product with a binary vector that is 0, 1, 1, the result that I'm going to get is a vector that is 0 when this binary vector is 0, and the value is equal to the original vector when this binary value is 1, right? So the gate layer works similar to this. It's as if when you have 0 in your binary vector, you are forgetting what was in your original vector. So you have a 0 in the new vector that you're going to have. And when you have a 1 in this binary vector, you are going to remember what was in the original vector. You're just copying the value of that original vector there, right? So in LSTMs, this is as if this original vector is our hidden layer, and this binary one is our gate layer. So this is a gatekeeper for what to remember and what to forget. So we do have this selective read and write operation to store the values and read some values and write to output when those values are needed. So this is an element-wise product. So it's basically a kind of multiplicative layer that we have, and as a result, it's not our the resulting LSTM is not going to be a fully connected network anymore, and we are going to see that architecture very soon. So because of this kind of memory situation, the name is coming from the long and short-term memory. So it's basically going to keep a long set of dependencies, but they're going to be stored in a short-term memory, and they're going to be used later. The values that are in the gate layer, the zeros and ones, for example, the network is going to learn these values. So the network is going to learn which values it should remember and which values it should forget. So that's how we are going to know what to set in this gate layer. But the problem is that if we use strictly the zeros and ones, the problem is that when we want to take the gradient and do the back propagation, we cannot differentiate the zeros and ones. They look like a step function, right? In the step function, we had this kind of situation that the gradient was almost always 0, and it was difficult to differentiate and back propagate. So instead, what we do in LSTMs is that we replace this with a sigmoid function that it is close to 0 and close to 1 when we have larger absolute values, and only in the middle we have something that is not 0 or not 1, but at least it is differentiable. So basically these binary values are going to be replaced by values that are very close to 0 and very close to 1. So for example, this is going to be 0 0.01, this is going to be 0 0.99, 0 0.99. Okay. So this forget gate or forget layer, we show it with phi. So we are going to have a forget gate phi t that is basically going to tell us what to remember and what to forget. So how is it going to fit into our network? You remember that in RNN, it's in basic RNN, what we had was that we had HT or ZT is FH, the activation function, over WI XT. So this is the input layer multiplied by WI plus the WH transpose HT minus 1, the feedback that we are getting from the previous layer, plus BH. That was the feed forward that we had for basic RNN. Now, when we have this new forget gate or phi t, we are going to modify this hidden state and remember just part of it and forget some other part of it, right? So because of that, we are going to define a new vector. So we are going to define a new vector ut, which is basically, we call it the candidate update vector. So it's not going to be HT anymore. It's going to be UT. The value of UT is then FU, so the activation function for U, WI transpose XT plus WH transpose HT minus 1 plus BH. So you can see that it's very similar to HT in RNN, but here it is not our definite hidden state because after we calculate UT, we have to forget something and remember something else, right? So basically, it's just a candidate for us for the hidden state, right? So we have now this candidate vector, okay? Then how do we calculate the new hidden state? So this is RNN, this is LSTM. So how do we calculate the new hidden state there? Then what we say is that we say our hidden state HT is now equal to phi t element-wise product with HT minus 1 plus 1 minus phi t vector 1 element-wise product UT. Okay, what does it mean? It means that at the places where phi t is 1, I want to have the value of HT minus 1. So the hidden state, the previous hidden state, to be just copied to HT without any changes. And nothing from the UT or the candidate update vector is going to come into my new hidden state. So when so this is going to be like this. If it is going to be equal to ht minus 1 if phi of t is equal to 1. Otherwise, if it's equal to 0, it's going to be equal to ut. So if phi t is 0, then the only thing that remains is the candidate update vector. So we are just going to have a new update state that is calculated and is equal to ut. Of course, we said that our phi t is not always 0 or 1, it's something in between. So basically, our new hidden state value is something between the previous hidden state and the candidate update vector that takes into account the input at this time t. All right? So in other words, what we can say is that this phi t is going to be forgetting the 0 ones and remember the rest, right? So phi t is going to tell us how much of the prior hidden state to forget or to remember. So this is like how much of prior hidden state to forget. And this part is about how much of the current update to keep or remember. Keep, basically, right? Okay, so now instead of just having ht, we also have ut and phi t, and they're going to tell us how to update ht. Now, how to learn this phi t? Because we said that we are going to learn this forget gate, right? How to learn? Okay. All right. We decided already on the function for that, right? So we said already that we are going to have the sigmoid of something as the phi t. So this is the sigmoid function. And also, we think that the value for this phi t should be depend on h t minus 1, right? Because we are trying to decide if we are trying to forget or remember the previous hidden state or not. So I should know what is in the hidden state that I'm trying to forget or remember, right? Basically, it's what am I going to forget, right? So if I decide to forget something or not, it depends on what that thing is, right? And also it depends on the current input, because it is going to keep the update according to the current input, right? So we are trying to learn about this current time and what we are going to remember or keep. So what am I going to keep? And knowing that is going to help me do it better, right? So it's going to be a function of xt and ht minus 1. But how is this going to be applied? So actually, this is a function for now that we know depends on sigmoid. The actual function with all the parameters and all is like this. It's the sigmoid of, now we have a set of parameters for xt, w phi I transpose xt plus a set of parameters for the ht minus 1, w phi h transpose h of t minus 1 plus, well, a bias for it. Okay. All right, so right now we have defined lots of things here. So the phytis, the HT and U, all of that. Now let's see what this LSTM forget gate looks like inside the network. So the way that it looks like is like this picture. So what we have, oops, here. So what we have is the input xt and the candidate ut and the forget gate vt and the hidden state and the output. Okay, so what are these relations? First of all, we know that ut, the candidate for being updated, depends on our input xt and also depends on the hidden state at time t minus 1, right? So hence these two in ut. Additionally, we know that our HT, our H update, it depends on HT minus 1. So there is this inside loop with HT minus 1 with a parameter that is phi. So basically HT minus 1 and phi are going to have this element-wise product, and they're going to go feeding back into HT. On the other hand, the rest of HT is coming from the candidate, right? So phi 1 minus phi t is going to be multiplied element-wise with ut, and it's going to go back to ht also. So that's how we build ht. Now, the way that we calculate phi t was based on our input x and also based on what we wanted to forget, right? The previous hidden state. So that's the input into VT. And eventually we are having this output, which is similar to MLP and RNN. Okay, so that's how the forget gate works. But that is just part of LSTM. So LSTM, in addition to the forget gate, it has two other gates. So for LSTM has three kind of gate layers. One is what we have seen, the forget gate. Which is defined as theta w phi I transpose xi plus xt plus w phi h transpose ht minus 1 plus b of phi. The second one is the output gate. So again, this one is called omega. Omega t is sigmoid of, now it has its own parameters. So w omega I transpose xt plus w omega h, similar, very similar to the forget gate, transpose h t minus 1 plus b omega, and another one which is an input gate. and that is kappa T is sigmoid of W kappa I transpose xt plus W kappa H transpose HT minus 1 plus B kappa. Okay. So this is the full LSTM. We have 3 of these kinds of gates in full LSTM. Not all of those are necessary. There are different variations of that. For example, GRU or gated recurrent unit, it has fewer gates. So it drops one of these gates and it still works. It's simpler. But okay, going back to LSTM, we still have this candidate update vector U. And what we are going to do is that we are going to keep 2 types of memory. One is a hidden state, HT, from which the output is computed. So if I show you here, so we have a hidden state HT, that output is computed from that. But also we have an internal memory for long-term dependencies and long short-term memory, basically, that it has a long dependency, but it is going to be used in short term, and that is C. Okay, now CT is going to be calculated like this. CT is kappa T element-wise product with UT plus phi T element-wise product with CT minus 1. So what it's trying to do, and you can see it in the picture also. So it's basically the kappa T element-wise with UT, and it is the plus, it is with phi T element-wise with CT minus 1, right? So what it's trying to do is to think of, first of all, here, UT is the candidate update, right? It's coming from the input somehow. So it's thinking of how much of input should I remember. That's why this is our input gates. All right. And on the other hand, it is thinking of, because CT minus 1 is the previous internal memory, right? So it is thinking of how much of previous internal memory should I forget. So that's why we have this forgetting gate. Okay, and you see that for here, for CT here, we do not have any activation functions. No activation function is here. And because we don't have any activation functions, it's as if we are using an identity activation function, right? So we are not going to have any decays, and we're not going to have any explosion of gradients because of that. So that is very nice. From the other memory that we have. So we have also still a hidden state HT, right? Similar to what we had in RNN and MLP. So we still have HT. Now HT is now the memory that our output layer sees. Memory seen by output layer. So what we are going to have in HT is that it's going to think of two things. One is that, okay, output gates, like how much of the internal memory I want to use to write to my memory that the output is going to see. So I'm going to have this omega t, the output gate, element-wise product with tan h of the internal memory. So basically, this is the output gate. Basically, we are going to have a tan h over CT, and we are going to use omega t here and calculate HT, or the output layer, the memory that output layer sees according to that. This tan h is that it's just going to work better this way if we include the tan h. And eventually we are going to calculate the output OT, which is equal to FO, the activation function for that layer, WO transpose HT plus BO. Okay. So that's basically the full LSTM with 3 different kinds of gates that it has. Similar to RNN and multi-layer perceptron, what we are going to do for backward propagation is that we calculate the error, we compute the net gradients, and we start from the output layer and going backwards and update the gradients of the parameters to learn the parameters. So to compute the net gradients, we are going to follow a similar rule that when we want to take into account what part of nets go to a neuron, we consider the weights that are associated with that net gradient. So it's basically mostly very similar to the other deep learning gradient updates. So we are going to compute the net gradients deltas and then compute the gradients with respect to W's according to net gradients. So what we are going to have is we are going to have delta of OT, delta of net gradient of HT, net gradient of CT, net gradient for UT, net gradient for VT, net gradient for kappa T, and net gradient for omega T, right? So we're going to have all of these, and from those we are going to calculate the gradients with respect to WPI, the gradient with respect to W kappa I, with respect to W omega I, etc., etc. And then we're going to learn these parameters using gradient descent. So that is LSTM.